Okay, so if we want to do inflection points concavity, we do the second derivative set equal to 0. Well, that would be at 3 and at 5 in this graph. Now, you know, if you were working a problem, you wouldn't already have the graph up there, right? But just so we'd have an equation and we'd be looking for it. So we do the second derivative set equal to 0. We get 3 and 5. We put that on the number line. Then we plug numbers in between into the second derivative, and we get a negative, positive, negative. That tells us concave down, concave up, concave down. Sure enough, concave down, concave up, concave down. That's how we do a problem with chart stuff. Okay, number lines tell us everything we need to know. Okay, now let's shift gears, and the new thing now would be this over here. Okay, so let's say we had a problem where they wanted us to find the global max min of the function. First of all, one thing that'll be different is they'll usually give you an interval to look. Because think about a parabola. Say a parabola opens up. What's the global max on a parabola? The max, if it's going up. There isn't one, right? There isn't one. Global max is the highest and lowest point on the graph, right? There is no global max, but there's a global min, and that would be at the vertex, right? So it'd be a global min, but not global max. But if I give you a set of endpoints, I said only look at the parabola from 1 to 7. Now there would be a highest point, there'd be a lowest point. Okay? Now let's assume for right now that our graph has no sharp points in it. No breaks, no gaps. Remember we talked about continuous? So let's assume our function's continuous, but not only continuous, smooth. Now for smooth, we're going to have another term for that. It's called differentiable. But when we say it's smooth, that means no sharp points either. So no breaks, no jumps, none of that stuff, and it's got no sharp points. So we don't have to worry about the derivative being undefined for right now. Later on, we'll worry about that, but for right now, that's, I guess I'm not going to promise it won't come up. Not going to come up on the quiz, okay? All right, as far as having to worry about that in this problem. So, where could the highest and lowest point be? Well, it's got to be, I'm going to call those candidates. What are the candidates? What are the possibilities for where the highest and lowest points can be? Well, it might be where the derivative is 0, like right here. Or it could be at an endpoint, right? The highest point on a parabola going up would have to be at an endpoint, right? Because it can't go on forever, or it wouldn't have a maximum on forever. That's it. Think about it. I mean, draw any kind of picture you want that's nice and smooth, that never has breaks or any of that. As long as we know it looks like that, there's no other place the highest point could be, or the lowest point. It's got to be at an end, or it's got to be at a turnaround, right? Which would be where the slope is 0. So that's good, because that tells us those are the only places we have to look. Okay, so we do the derivative, set it equal to 0, and in this case, that would happen at 2 and at 4 and at 6. Right? The derivative is 0 at 2, 4, and 6. And our endpoints on this problem are 1 and 7. So those are the 5 possible places that we have a highest point and a lowest point. Now, how do you suppose we find out which one's the highest point and which one's the lowest? Pretend you didn't have a graph and all you had was the equation of f. What would you do to figure out which one had the biggest value, which one had the smallest value? Plug them in. But where would you plug them in? To the original equation, f. See, now that's different than the left side of this picture. When we're doing a number line, we plug those numbers into f prime, or we plug them into f double prime, because what we care about is if f prime is positive or negative, and if f double prime is positive or negative, because that tells us about increasing, decreasing, all that. But in this case, we're doing something different. We're wanting to find the biggest y value and the littlest y value. So we have to plug them into the original equation, but we first find where they possibly could be at. So we find our candidates, which are at these 2 places here. So we have 5 of those. And then we come over here, and this is the LOC, stands for list of candidates. I'm going to make a list of my candidates and see what their y values are. So we plug a 1 into the original, we plug a 2 in, we plug a 4 in, we plug a 6 in, we plug a 7 in, and we see what output we get. The biggest output is the max. Well, in this problem, it's going to be at 2, whatever that happens to be. And the littlest output is going to be over there at 7, and that's going to be my min. These problems, we give the y value as our answer. Okay, we want, when it says what is the global max min value, we give the y value. For local max min, we don't say what is the local max min. What do we say? What's the question always? Where is the local max min? And then we want the x value. right? We want it, the local max is at x equals 2 and at x equals 6. The local min is at x equals 4. So we say, where is the local max min? We ask, what is the global max min? We want the outputs from the original function. Okay? So both are max min problems, but they're two different types of max min problems, so we got to understand the difference. Okay? All right. So, that's a problem we already did. That was 3 through 12. That was on homework there today. Okay, you don't have to write this down. This is a problem we did right before Thanksgiving when we were reviewing for the quiz, or when we were first learning. This was number 19 in section 2.4. And we were looking for local max, local min. So I just put this up here as a quick review to show you. So what did we do? Here was f of x. So we did our power rule. We did our f prime, which was this, right? And no, we would not do the definition of the derivative here the long way, right? You talked about that. Well, the only time you would ever do something the long way would be when it says use the definition of the derivative, right? Well, for you guys that are done with the quiz, we're past that. We probably won't do that much anymore, okay? We're going on now to our shortcuts. So you guys have to take a quiz. You still get to do some of that, but on the quiz. But now we're into the shortcuts, right? We're just using our derivative rule. So 3x squared minus 6x, the derivative is 5, of course, is 0, so that goes away. And then don't forget, we got to set that equal to 0. Okay? So then we factor it out, we solve it, we get our stationary points. We put f prime, so let's see, -1 and 1 and 3 maybe. Put -1 into here, you get negative into negative, that's positive. Put a 1 into here, positive, negative. Put a 3 in here, positive, positive. Okay, and so now we got all the stuff we were talking about over here, and now we can do, and we can go on and on. Now, let me add to that the idea of an inflection point. So let's say this problem had also asked about concavity. It didn't when we did it, but it could have. So what if it asked for inflection points, stuff like that? Well, we would then do f double prime, and we would repeat this process. So what's f double prime here? Minus 6, right? The derivative of a plain old x is just the number in front because that's a slope. The slope of 6x would be 6. Equals 0. So x would equal 1. That is a pip, possible inflection point, right? Back to the chart. When f double prime is 0, that's a possible inflection point. How do we tell? We put it on a number line, right? Same thing. We want to know, if you go to the chart, we want to know if f double prime, so we're looking at f double prime is 0, is a possible inflection point, but we got to change concavity, so we're looking for f double prime changing positive to negative. So we want to have a, check our number line. So let's put 0 and 2, let's put them back into f double prime. So remember, we were talking about listed candidates, we go back to the original, that's not what we're doing here. We want to plug these numbers into our second derivative to see if our second derivative is positive or negative. So we put a 0 into here, we get -6. We put a 2 into here, we get +6. So that means our f graph is going concave down to concave up. So we have an inflection point at x equals 1. And we would say, if this was a quiz, we would say f double prime changes. And I told you on the quiz, you had to do this, right? If you're doing a local max min problem, you have to say, this is a local max because f prime changes positive to negative, so therefore f changes from increasing to decreasing. Well, here, f double prime changes positive to negative, so f changes concave down to concave up. Now, with inflection point, we don't care which way it changes, so you could just say f double prime changes sign, so therefore f changes concavity. That would be enough, okay? So we do have an inflection point at x equals 1. Okay? All right, so number line for f prime tells you increasing, decreasing, local max, local min. Number line for f double prime tells you concavity and inflection points. There it is. That's all the chart stuff. That's what a problem would look like doing chart stuff. Okay, so that's this side over here. All right, now let's do one that's a global max min. So this one you might want to write down. We haven't done this one. This is number 23 from that same section. Okay? We're going to do one with sines and cosines here a little bit later, okay? But let's just go through one of these, okay? So notice the difference now. I give you a function with a fixed domain. So now the question is, find, now sometimes they don't use the word global. Sometimes they just say find the max and min values, so that we assume that means global max min. Okay, find the max min values means the global max min. Because we never want the local max min values, we want to know where they are. So we never ask the question that way. So, find the max min values of this function on the interval 0 to 2. So find its highest point, find its lowest point. Okay? All right. Like if we were doing profit, right? We might want to find what's the highest profit and how many things should we manufacture to get the highest profit. So we do the derivative, it would be 3x squared minus 3. Because what are we looking for? Why are we doing the derivative? I joked with you earlier in the year. I said, sometimes we say, if you don't know what to do the derivative and set it equal to 0, right? Well, on local max min, we do it so we can do a number line. For here, we do it so we can do a list of candidates, right? Where can our global max min be? Derivative 0, stationary point, or endpoints, right? That's it. That's the only two places they can be. Okay? Until we bring in the derivative undefined, like at a sharp point, you could have a low spot or a high spot at a sharp point. If we brought that in, we'd have to check where the derivative is undefined. But right now, we're not messing with it. Okay? All right. So we're looking where the derivative is 0. So we do the derivative set equals 0. This is why we have to be able to solve equations, right? Like we practiced on our worksheet today. So I factored out a 3, which I wouldn't have had to. I went ahead and factored it, but that's going to be plus minus 1. You can't forget the plus minus. You could have added the 3 over, divided by 3, get x squared equals 1. Square root it, but remember you got plus minus then. Okay, so we got two stationary points. So here's my list of candidates. So I come over here and I make a list of candidates. If you label LOC, we'll know. And if you do that on the AP test, I think they're going to know. This is considered to be valid justification. A list of candidates here is valid justification for finding this. So I'm going to put 0 back into the original. I'm going to get 5. I'm going to put 2 in here. 8 minus 6 is 2 plus 5 is 7. Put a 1 in there. I get 3. Put a negative 1. Is that 7? So what's my max? What's my max? 7. What's my min? We want the output, right? We don't care that it happened twice. That doesn't matter. The highest value, the max of this function from 0 to 2 is 7. Did I do that right? Did it happen twice? You just did that. Okay. But notice I put it back into the original. That's why I think it's so important to label them here. Label your number lines, F prime and F double prime. That reminds you where you're supposed to be plugging your numbers into. When you do your list of candidates, do F of 0, F of 2, F of 1, F of negative 1. It reminds you you're plugging them into F. Yes, sir?
Do you need to do F of negative 1? No.
Great question. Do you need to do F of negative 1? No. So that was, matter of fact, what if F of negative 1 would have come out 8? And then I would have put 8 as my answer. I would be wrong, wouldn't I? Because it's not in that interval. So once I got negative 1, it probably would have been appropriate to just throw it away right here. Just throw it away. We don't even want it. Okay? Should not have put it in there. Okay? I think at one point I put it in there to just to see if anybody caught it. But to be honest, I didn't catch it. I don't even think.
So how do you know what numbers to use for your list of candidates? In between that,
it comes from here. Here's what you use. F prime is 0, which are stationary points, and your endpoints, which are those two numbers there. Usually, that's how you know. Okay? So it goes back to this picture here. Our candidates are the things we use in our list of candidates, right, are anywhere the derivative is 0 and the endpoints. That's what goes in our list. Okay? So that's why we started the problem by doing the derivative and setting it equal to 0. Because we wanted to find those candidates, and then our endpoints are usually just given to us. Right? The endpoints usually are just given to you in the problem, so that's nice. Okay? And then you plug those in. And again, the reason we're confident that those are the only places the maximum can be, because just picture a graph. Think about it. Try to draw a graph where that's nice and smooth, where the high spot and low spot don't happen either at an end or at a turnaround point. It has to. Otherwise, you'd have to have jumps or breaks or something weird going on, right? It has to happen at those spots. So that's why those are the only places we check. Okay? All right. So let's take a look at this one. Okay? So a lot of times this problem would have been given here like this. Okay? So, right, so this is a little stranger looking function, and we want to do the list, we want to find the global max min on the interval 0.25 to 1. On the interval 0.25 to 1. Okay, so we're going to do the derivative. So I'm going to write it as x to the 1/2 and 3x to the -1. Right? So we got our endpoint. So those are two. So Daniel, back to your question, those are two of the places we're going to check. Right? The other places we're going to check is where the derivative is 0. Stationary points. So we're going to do the derivative. We bring the 1/2 down in front. Drop that by 1. So you see why we got to be able to do this power rule. Right? We got to be able to do that, right? We got some work to do on that still. Bring this -1 down here, which makes that, turns that negative into a positive, and then that drops to -2. Now we got to solve this. So this is where that practice on those solving equations would be kind of important. So the question would be, now is this a calculator problem or a no calculator? If it was a calculator problem, we would just go ahead and solve this right now. So let's go ahead and do it like it was a calculator problem. Okay? So go ahead and get your calculators out. Should have a presenter today. All right, so what are we wanting to do? Tell me when you're logging in. You're good? Okay. Oh, you know what? I'm not. That's my bad. All right. Now I'm going to show you something that's going to be really important now as we, okay, now. Enjoy. False. You're getting false?
Yeah.
All right. All right, so we go. Okay, so we go to algebra, solve, and so he's typing it in here. We got 1/2 x to the -1/2 plus 3x to the -2 equals 0. But I'm going to show you something here that's really important, and on these global max-min problems especially, okay, and trig problems especially, and that is because Okay, so it says false. So what that tells you probably is that this never does equal 0. Okay, that's fine. Maybe it doesn't. So that means we have no stationary point candidates. The only candidates are the inputs. Okay, now, but here's what I want to show you. Because it's possible that you would get like 10 answers here, and only one or maybe a few would be inside of our interval, like Jace was saying, hey, we got to throw those out because they're not in the interval. You can make the calculator look in your interval. I think I showed you this with the vertical bar. Didn't I show you guys the vertical bar thing? I think there was a problem where we did this. Well, this is where we really want to do this. When we want to only look between 0.25 and 1, so outside the solve, so you got to go all the way outside the solve parentheses. The vertical bar is above the equal sign here, so control equal sign. Grab the vertical bar, that means with or such that, and now go 0.25 less than or equal to, so that's under the equal sign as well, control equal. Let's do less than or equal to, because I think it was a closed, no, less than or equal to. It was a closed bracket, and then X, and then less than or equal to, and then 1. And so on our next quiz, you may have to do this. Probably, for sure, we'll have to do this. Like on a sine or cosine one, we may look between 0 and 2 pi, or 0 and pi, or negative 5 to 5, or whatever. We'll probably have a close. And where it's really important with sine or cosine is you get those infinite ones. You know, that's when you get that weird answer like pi 6 plus 2 pi n, blah, blah, blah. It looks just like a mess. That's going to make it real confusing for you if you don't do this. If you do this, go ahead and hit enter. Then it'll just give you the ones you want. Now, this says false. So what that means is there aren't any places. Okay? So we come back to here, and we say, okay, no stationary points. And we should write that on our paper. We want to communicate the fact that, hey, we don't have any of those candidates. So our list of candidates is going to now be f of 0.25 and f of 1. Okay, now let me show you another little calculator trick here. Now, again, depending on how comfortable you are with the calculator, you can do this or not do it, doesn't matter. But we just need to plug in a 0.25 and a 1. So if we go back to the calculator here, let me show you, especially if you're having to plug in several values. So what you can do here is arrow down, go ahead and arrow down. Now we got to put in the original function, right? The original function is what we want to plug it into. Now, the original function, we can use our 1/2 powers, but those are harder to plug in. It was square root of x minus 3 over x, right? That was the original function. So right now, Kobe could go, don't do it, but he could do square root of 0.25 minus 3 divided by 0.25 and just do it, right? And then put in a 1 and just do it. Now, the 1 is probably easy enough to just do in your head, actually. Okay, but let's say we had some weird numbers to plug in and it was a pretty complicated function. Here's something you can do. So Kobe, just type in square root of x, and then right arrow, and then minus 3 over x. Yeah, do the fractions better. And then right arrow, and now the vertical bar. Now, where people screw this up is they put a solve in front of this. We're not solving anything. We're just wanting to plug in something for the x. So don't put solve there. Solve is when you have an equal sign in it, right? You're doing this equals 0 or something. So we're not solving, we're evaluating. So we're taking this expression, vertical bar reads with, and now put x equals 0.25. And what this is going to do is it's going to stick a 0.25 everywhere the x is. Hit enter. Okay, and now here's the beauty of it. Arrow up and grab it, hit enter, and now delete the 0.25 and now put in the 1. And if we had like 4 or 5 things to plug in, this would be really fast, right? And you could just grab it. So that's something to think about. Again, we don't do a solve when we're doing this. It's not a solve. All right, so negative 11.5 and negative 2. So negative 11.5, negative 2. Here would be our max. Sometimes we just do it this way. Here would be our min, right, like that. And it turns out that this just is always increasing. This graph's just always increasing. It has no stationary points. It has no place for root 0. So the left edge is your minimum and the right edge is your maximum. Makes sense. Okay. All right. All right, moving on. Moving on. So that's global max min. That's global max min. List of candidates, that kind of thing. All right. Now, I would start a new piece of paper. Now, at some point, we're going to probably start another new piece of paper with derivative rules. And at some point, I'm just going to give you a sheet with all the derivative rules. But I think it's a little much to give that to you right now. Okay? It'd just be a little overwhelming. Okay? So, let's write down some derivative rules that we have so far. Okay? Let's start with some real simple ones. Derivative, remember our Leibniz notation? What's a derivative of a constant? What's a derivative of a constant? K. 0. What's the derivative if we add or subtract two functions together? What do we do to get the derivative? So you just do the derivative of the first one plus or minus the derivative of the second one, right? Yeah. So now, why is that important to write as a rule? Well, does it work if you're multiplying two functions to just do each one of them individually? We said no, it doesn't work. Okay, we tried that. We did x squared times x cubed and did each one of them, and it didn't work. It didn't give us the right answer. So this is an important rule. If you have two functions added or subtracted, you just do their individual derivatives. So those are a couple of rules we have. Here's another rule we have. We haven't ever written it out in this form. What if you have a number setting outside of a function? What if you have like a 3 in front of an x cubed? What do? You leave the k there. Now this isn't that kick out thing. That's when you have something on the inside. We'll get to that next. When you have a 3 on the outside of x cubed, what do? The 3 just hangs out there, and then you do the normal derivative, right? So if you have a number multiplied outside of a function, so what's the derivative of 3 sine x? 3 cosine x, right? The 3 just hangs out there, and then you do the derivative of sine, which is cosine. So if you have a constant in front of a function, the constant just hangs out there, and you do the derivative. Okay, now, here's the one you're talking about, I think, Harish, is what happens if you have something multiplied inside times the x. You have to kick out that k, and you leave it on the inside as well. So you do the derivative, that's the f prime notation saying we do the derivative, we leave the inside alone, the k that we're multiplying stays in there, but we also have to kick out that k, right? That's where we're talking about sine 2x. What's the derivative? Well, it's cosine 2x, and with a 2 out in front. You have to kick out that 2. So that's a rule we've talked about. Okay? All right. And then, of course, we have our power rule. X to the n is n times x to the n minus 1. So there's our power rule. We know that the derivative of sine is cosine. We actually know the derivative of cosine too, don't we? What was the derivative of cosine, remember? It was negative sine. It was negative sine. We kind of did that with slopes and we looked at it. Okay, so now it's just something to memorize. Just something to memorize. Now this list on the left, we're not, these on the left, we're not memorizing. I mean, kind of, but I think we kind of know that. So it's power rule is easy, right? I mean, so most of these, we say we're going to have to memorize all these, right? Well, it's quite a list already, but I'm not so sure we don't know all these already. We got to practice and we get better at it, but whatever. Okay, there's another one we know. What's the derivative of e to the x? It's its own derivative, right? That was kind of a cool thing we said about e, that it was its own derivative. Now, if you had a 2 inside there, e to the 2x, the derivative would be e to the 2x, and kick out a 2, because there's a 2 on the inside. That's the inside of e to the x function. So e to the 2x, the derivative would be e to the 2x, its own derivative. Leave the inside alone, because we always do. And then take the 2, kick the 2 out front. 2e to the 2x, right? So that's some of what we're going to be practicing here as we go through this chapter. Okay? All right, that's pretty much it. That's pretty much our rule at this point, our list of rules at this point. Okay? All right. So, you might jot this down. This is optional, totally optional, but we're talking about having to solve. We're going to get into exponential log and trig equations. There are a couple of IXLs under pre-calculus. Just, again, you already had that worksheet as practice. So this is just, there's extra stuff. If you, especially the trig ones, maybe, if you want to practice solving some trig ones. And this, I might have had this up as an optional, one of the things we did earlier this year. I'm not going to grade it. It's just totally for you. If you want, think you're going to practice. But I'm promising you on the next quiz, there's going to be a trig solving, probably both on the calculator and the no calculator, right? So we've got to be able to do that. So that's some extra practice.
So when you say trig solving,
okay, so that would be like this right here. So say we do a derivative. Say we had 2 cosine x minus x was our function, right? And we wanted to find the local max and mins and where it increases and where it decreases, right? Well, where do we start? If you want to find the local max min, what do you do? Do the derivative, set it equal to 0. So f prime would be, derivative of cosine is what? Negative sign. The 2 out in front, what do we do with that? Keep it there. So we have negative 2 sine x. What's the derivative of x? 1 minus 1, right? Minus 1, and we set it equal to 0, right? So then what are you going to do? You're going to solve that. You're going to divide by negative 2. So your stationary points are going to be where sine equals negative 1/2, right? So now you're going to have to know negative 1/2. Oh, sine's negative down in the 3rd and 4th quadrants. That'd be 7 pi 6, 11 pi 6. Those are my 2 stationary points. If it was a global max min problem, you would take 7 pi 6, 11 pi 6. Those would be 2 of your candidates. You would plug those back into the original, right? So you'd have to be able to do cosine of 7 pi 6 and know what that is, right? Right? We'll practice that, but that's what I'm doing. Okay? Yep. All right. And sine and cosines are great problems for local max mins. They got all kinds of them, and inflection points and concavity changes, right? So those are great problems to do those kind of things with. All right, so let me show you this. Don't write this down. I just want to just briefly, just for time, I don't want to mess a lot with it. But, you know, why? We said that e to the x was its own derivative, and we did it by just calculating some slopes, and we're like, oh, wow, the slope is coming out to be exactly the same as the y back. Amazing. The slope is the same as the y back. Okay, so that's how we knew that. But a mathematician would want a little more proof than that. So it would all come back to the definition of the derivative, right? We would do, if we want to show the derivative of e to the x, we have to come back to this, right? And so what's that mean? Well, we take x plus h and put it in right there. We take x and put it in right there. So that would give us this, right? So that would look like this. But now there's no algebra. Well, there's no obvious algebra that we can do to this, right? As far as our bow tie and the algebra we were doing. Okay, so what could we do? Well, we could do this right here. Okay, isn't it true that e to the x times e to the h, wouldn't the rule be that you would add those together? Isn't that the rule? So we can do that in reverse, right? We can take e to the x plus h and we can split it apart like that, right? Makes sense? Okay, so now we do that. Well, now what can you do up here? Factor out e to the x. So we factor out e to the x, okay, so that's this one right here. So we factor out e to the x and we get this. Now, as h is approaching 0, this is changing, right? These things are changing. What's happening to this as h approaches 0? Doesn't have an h in it. Doesn't have an h in it. So as h is getting closer and closer to 0, e to the x is not changing. E to the x is just e to the x. So we can actually take the e to the x and we can actually take it out of the limit because it's not affecting the limit at all. And all we really need to do is the limit of this. Well, if we could do it, we could do a calculator table. We could do a lot of different things. Of course, if you try to plug in a 0, you get 1 minus 1, you get 0 over 0, so that's no good. But if we would look at a calculator table, we would see that the limit of this is approaching 1. The table, the outputs are getting closer and closer to 1 as h goes to 0. So you get 1 times e to the x. E to the x. Sure enough. It works. So the derivative of e to the x is e to the x. I just want you to see that because you got to understand that every derivative eventually comes back to that, the definition of the derivative. Okay? All right. So let's do this problem right here. Okay? So let's think about our new rules we were just talking about. Oh, shoot. There's a rule in there I didn't tell you about. Okay? I just noticed it there. Okay, let's go back to our rules. I got one more rule to put down here. I'm not going to give you the log rule right now. Okay? What happens if we have a different base? What happens if we have like 2 to the x or 3 to the x or something like that? Well, it turns out that it's almost its own derivative. E to the x is the only one that's its own derivative. But it's b to the x and then times the ln of b. So if it was 2 to the x, the derivative would be 2 to the x times ln2. Remember, ln2 is just a number. ln2 is just a number, right? So it's 2 to the x times ln2. If it's 3 to the x, it'd be 3 to the x times ln3. Okay? And actually, it works for e to the x, right? Because this would be e to the x times ln e. What's ln e? 1. Right? So e to the x times ln e. So that rule would actually work for e to the x, but ln e is just 1. Okay, so back to this one. Okay, so take what we've just learned, and you guys write down what you think f prime would be. Taking into account all the stuff we've talked about if you're multiplying by something on the inside, you have to kick it out, how we always leave the inside alone, right? That kind of stuff. All right, well, if you know, you probably know if you're done. If you don't know, you're probably not. No more time's going to help. That one's easy, right? 6x to the first. What about this one? Minus 2 cosine 2x, right? Derivative of sine is cosine. Leave the inside alone. Kick out the 2. Plus 3 to the 4x plus 1. Now, I put parentheses around that to emphasize that that's the inside, but a lot of times there would not be parentheses around that, right? But you understand that's the inside of that function. Is that it? Times an ln3. And that times takes precedent over this plus. We wouldn't have to put parentheses around this. We're really going to have to be careful with parentheses when we do these. But these are grouped together, but because times takes precedence over the plus, it would. Okay, but that's a different base. Now, if that was e, now I'm still not done, though. That one's still not done. We got to kick out something. Didn't we times on the inside by something? If you multiply on the inside of a function, multiply the x on the inside of a function by some number, you have to kick out that number. So we have to kick out 4. Okay, and that's when I say kick out, multiply by a 4. Now, a lot of times we would move that around front. Okay, we put 4 ln3 times 3 raised to the 4x plus 1. That's just rearranging, so not a big deal. Okay, and no, we cannot take that 4 times that 3. That doesn't work. Not when it's got a power. Can't do it. Okay, so we can't forget about kicking out that 4. All right, so you're going to have some practice on those. Matter of fact, there's going to be some problems where they're going to say, okay, here's a function, do the derivative, and then a later problem is going to be do the second derivative. Well, what do? You just do the derivative again, right? Just do the derivative again. Take a crack at it. Take a crack at it. Write down the second derivative. All right. What's the derivative of 6x? 6. What's the derivative of cosine? Negative sign, so that's going to turn to a plus. What do we do this too? Leave it there, right? It's going to hang out there. But then what are you going to do with this 2? You kick out, so what are you going to have there? 4 sine 2x. The inside always stays the same. So derivative of cosine is negative sign, so it turns to a plus. 2 still hanging out there. We kick out another 2. 2 times 2 is 4. Okay? What about this? Now, again, this looks like a mess, but remember, these are just numbers. 4 and ln 3 are just numbers, so they're just like this. When you have a number times a function, the number just hangs out there while you do the derivative. So the ln 3 and the 4, as a matter of fact, I'm going to bring those around front. So the 4 and the ln 3 just hang out there. So all I'm really doing the derivative of is this. Well, what is that derivative? What's the derivative of an exponential? Itself times ln 3, and we'll have to kick out a 4 again. Okay, so the derivative of just this piece is just like we did up here. So I'm going to have 3 to the 4x plus 1. Inside always stays the same. And then I'm going to have times an ln 3, and then times another 4, which I guess I could scribble that out, make it a 16. I could make ln 3 quantity squared if I wanted to, whatever. But right, I'll have to kick out another ln 3 or another 4, and I'll have to tack on an ln 3 because that's what you do when you do the derivative of that thing. But these two things just hang out there because they're just numbers multiplied by something, right? Now sometimes people get confused when we talk about here, the derivative of a constant is 0, so sometimes people think, well, the derivative of 3 is 0. No, that's different. The derivative of a constant all by itself is 0. But if you got a constant in front of some x's, that's a different story. Now it just hangs out there. Okay, so that would be the derivative, the second. Okay, so we'll get a practice out. All right, let's do this problem right here. This is from page 147. This is similar to probably some sort of problem. I said we're going to have to do a trig one, so let's do it. Okay, trig kind of thing. So this is on page 147, number 35. Here's the function. The questions, there's a whole bunch of questions, A, B, C, D, and E. Are there any stationary points from 0 to 2 pi? Where is f increasing? What are the max and min values from 0 to pi? Where's this concave down? Where is it increasing most rapidly? So when I see things like that, right away I'm thinking, okay, it's a chart. I heard inflection point, so I'm going to have a concave down or something. So I'm going to have to have second derivative. I'm going to have to do a list of candidates. Of course, that means where the derivative is 0. So we're doing all of it in like one problem. Well, so I'm going to need f prime. I'm going to need f double prime. I'm going to need where there's 0. So I might as well start there. Let's get that information, and then we'll start talking about the question. Okay? All right, so what's f prime? 1 plus sine of x. And we set that equal to 0. Now, remember, we're talking about 0 to 2 pi in part of this problem, and part of this problem, they were just talking about 0 to pi. So, depending on which part of the problem we're in. Okay, so I got to solve that. So sine of x equals -1. So where does sine equal -1? Now you have 2 ways to do that. You can think of the sine graph, right? That's a pretty easy way to think where it's -1, or you can think of the unit circle. It's up to you. Sine remembers the y value. Sine's the y value in the unit circle, so it'd be down here, right? So what is it? 3 pi over 2, right? 3 pi over 2. We got to know that. Got to know that. Got to figure out a way to know that. Come in, get help from BPD. So that's it. Remember, because on this part we were just looking 0 to 2 pi. So there's my stationary point. So it didn't talk about local max min, but it's part A said doesn't have any stationary points. Yes. If so, where? So there's our answer to part A. Right? So part A, were there any stationary points? Yes. X equals 3 pi half. Okay? B says, where is F increasing? So what do we need to get that? Number line. Let's do a number line. We want to know where F prime is positive. We only have one stationary point to put on our number line. So what would be a number less than 3 pi halves? Do we really want to plug 1 in, though? Because we're going to plug it into here. What would be a good number to plug into sine that's less than 3 pi halves? Pi, or pi halves. Okay, what would be a number bigger than 3 pi halves? 2 pi. And we can, that's right on that's on the edge of our domain, so we can use it. Okay, so let's put pi into here, into F prime, right? So sine of pi is what? 0, that's the y value, sine of pi, or you can go to your graph right here, sine of pi right there would be 0, plus 1 is 1, so that's positive. What's 2 pi? What's sine of 2 pi? Also 0. Oh, so also positive. So where is this graph increasing? Part B was where in 0 to 2 pi is F increasing? 0 to 2 pi. Everywhere, right? 0 to 2 pi. It's always increasing. Okay? So we must have what right here? Flat spot. A flat spot. Right? C, find the max and min values of F. Okay, that's our list of candidates. That's our list of candidates. We plug those back into the original. So which ones? Now this said from 0 to pi. So what are our candidates, Daniel? Where the derivative, that's the endpoint. What, 0 being an endpoint, or where the derivative 0, which we type? Being an endpoint. So 0 is one of them. So here they said 0 to pi. So we're going to plug in 0. We're going to plug in pi. Where else are we going to get? What else are we going to plug in? 3 pi halves. Jace, we're going to plug in 3 pi halves? Why not? It's not in the interval. It's not in 0 to pi. But normally you're right. Normally you're right. We would look where F prime is 0. Right? We would do F prime is 0 at 3 pi halves, but it turns out that it's not. Now, to be honest, what did we just learn on the number line? The graph's always what? Increasing. So where's your high point going to be? At the right endpoint. Where's your low point? Left endpoint. Now, whenever you do a global max min prime, you've got to justify that it's a global max min. Now, list of candidates is normally our justification because it works every time. Well, it works most of the time, and it's good enough to be a justification. So if we do that most of the time, we can. But we don't have to do a list of candidates. We have to have some justification. So on this one, I could say, since F is always increasing in the interval 0 to pi, the minimum would be F of pi, F of 0, and the max would be F of pi, and find those values. Make sense? You just have to justify that it's a max min. Since this is always increasing, we can do that. But anyway, we won't use that, so let's plug it in. Now remember, we got to plug this into the original. Okay? Because this is F. We were trying to find the F output. So we put a 0 in. We got 0 minus cosine 0. What's cosine 0? 1. 0 minus 1 is -1. Put in pi. What's cosine of pi? What's cosine of pi? Cosine's the x, remember? Cosine of pi, -1. Remember what the cosine graph looks like? Looks like this, right? Cosine of pi is right down here, -1. Okay? So, cosine of pi is -1. So we got pi minus -1. That'd be pi plus 1, right? Which is about 4.14, whatever. So for comparison purposes, that's clearly the max. So the min is here, the max is here, Now again, I just circle the y values. That's all I care about. It said, what are the max and min values of f on the interval 0 to pi? Okay? All right, D. Where is f concave down? What do we need to get concave down? Need f double prime. So let's do the derivative of 1 plus sine x. What's the derivative of 1? 0. What's the derivative of sine? Just cosine, right? So we need to know where is cosine 0. Now, again, we're back in the interval 0 to 2 pi. Where is cosine 0? Remember, cosine's the x. Pi halves, 3 pi halves, right? Or where does cosine equal 0? Right there at pi halves, and right there at 3 pi halves. So x equals pi halves, 3 pi halves. Those are our possible inflection points. But they didn't ask for that. They asked, where's f concave down? So what do we need to get that? Number line. F double prime number line. We're going to put pi halves on it, and we're going to put 3 pi halves on it. And wherever it's negative, that's going to give me where this is concave down. So 0 would fit good in there, pi would fit good in there, 2 pi would fit good in there. Okay, so we got to put those where? We got to put those back into our f double prime right there. Right? Because we're trying to see where f double prime is positive or negative. So we put a 0, cosine of 0 is 1, positive. Cosine of pi, negative 1. Cosine of 2 pi. Well, heck, the cosine graph, we know where cosine is 0. Heck, the cosine graph tells us it goes positive, negative, positive. That is the cosine graph is our f double prime graph. Positive, negative, positive. So where's this cosine? So where's this concave down? Concave down from pi halves to 3 pi halves. Now we need to organize our answers a little better than I'm doing here, but you get the idea. No, always on the chart stuff we do close parentheses. Okay. Or open. It actually doesn't matter. To be honest with you, I actually said that wrong. I think on chart stuff I've said in the past, I think I've always said open parentheses, actually, have I? Why do I always say, let's see, I've been teaching 20 years. All of a sudden I can't remember. Open parentheses. Chart stuff we're doing open parentheses. So even back on this. Now, that's never going to get counted against you, though, on a chart question. Okay, but I think open parentheses. And then last thing, it says, where is f increasing most rapidly? Where is f increasing most rapidly? Evaluate f prime there. Well, where is something going to increase the most rapidly? At an inflection point, right? Now this one goes, and we're going to want it to be, and you don't want it to be this situation, right? You don't want it to be concave down to concave up because that's decreasing. You're going to want concave up to concave down, right? Concave up to concave down. So it's going to be at x equals pi halves. Okay? Because the graph's always increasing. So this graph's going concave up. It's always increasing. It's concave up. Then it switches to concave down. And then it switches to concave up. Right? Well, there's your inflection points right there. Well, this inflection point was a flat spot, right? We said at 3 pi halves, we had a flat spot, right? 3 pi halves was a flat spot. It's also an inflection point. Well, that's not where it's increasing most rapidly. It's going to be that one right there. Concave up to concave down. So it's at x equals pi halves. And then it says evaluate f prime there. So they want you to take that and plug it into there, into f prime. So what's sine of pi halves? Sine of pi halves is 1 plus 1. Okay? A lot of stuff in that one problem. And understanding, look at that, we got 3 different equations there. We plugged into all 3 of them, depending on what it is they were asking us to do. Okay? So, a lot of stuff, the chart stuff, the new idea about global max min, all that. Okay? But now, on the next quiz, I'm not going to probably have one question that asks all that. I'll probably have multiple different questions that ask a couple things in this one and a couple things in this one. Because again, if you get off track somewhere on this one, then man, you can just lose a whole. You can just get off on a whole bunch of stuff. So probably better to break it up into some pieces. So, all right. So on your homework, right after where it says solving equations review sheet, okay, those next two that are grouped together, 2.6 and 2.7. Okay, I think it's these problems right here. The E means even, if you didn't know. A lot of those, on those even ones, a lot of what those are, they're not as long as that last problem we did. Those even ones are the ones where here's a function f, you find f prime, so you do f prime. So using our shortcuts, using our new rules, and then f double prime, then they ask for f double prime. So those don't take real. Oh shoot, two more derivative rules. I'm sorry. Let me just throw them up here. They're in your book. You can look them up. I forgot that. I think the book is going to. They may ask you about these. So we did exponentials and we did some basic trig ones. Now, if they ask you about tangent or any of the other trig functions, they're in the section 2.7. So you may have to look at them. I don't think they do, so I don't think you have to worry about it. But if they do, just look them up. Just turn back in the section. This is very similar to the exponentials. Derivative of natural log. Now, this is kind of interesting because trig ones, it's funny. If you do a trig derivative, it's another trig function. If you do an e to the x derivative, it's another exponential. It's e to the x, 2 to the x, you get 2 to the x. Log's the only one where you don't. You don't get a log as part of your derivative. So if you're doing the derivative of ln x, it's just 1 over x. If you do a log of any other base, it's still just 1 over x, but then you have to tack on this 1 over ln b. Kind of like with b to the x, you have to tack on an ln b. Here we tack on a 1 over ln. Okay, so those are two more derivative rules for those two functions.
Do you get these like run on the AP test, or do you have them memorized?
Yeah, we'll memorize. We will have these memorized before Christmas. Right. We will do one of our quizzes. We have the one after our next one, is going to be just derivative rules. 10 problems, find the derivative. Okay, so we'll talk more about that later. Trust me, we'll use them so much that you'll have.